Oh, look at this kind of red shadowing. That's from my red pen. You can almost see where I wrote it last week. Okay, so we know that gas particles actually take on the shape and the volume of their container. Liquids take on the shape, but not the volume. Gases take on the volume and the shape. So 4 things we need to describe a gas are, and I usually do them in this order, because actually when we come to the ideal gas law, which we're coming here in a minute, that takes those 4 variables, they're in that order, P, V, N, and T. Okay, so we need to know those things in order to characterize gas. And then actually we had been talking how you can take a pair of them and make sure you hold the other 2 constant, and you can see how they vary. So we're actually going to kind of pick up with that. So this is actually the third of 3 laws, gas laws by guys. This is Avogadro's law. And we said Avogadro's law links volume with number of moles. And I told you that there's this cool thing that means that you can do with it. So for instance, in this case, we have the same number of moles. If I were to count those, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. So I'm trying to tell you, as long as these are at the same temperature and the same pressure, if we have the same number of moles, they're going to occupy the same volume. Right. Oh, that's not right. Wow, how did I do that? Go back. Go way back. Watch this. Monday. That's where I thought I was. My bad. Avogadro's law. That links volume with number of moles. So we did this with, I think, water, and here we're doing it with what's called the Haber process, making of ammonia. So if we know that this is the balanced equation, 1 mole of nitrogen reacts with 3 moles of hydrogen to form 1 mole of ammonia, then we can look at it visually like this, but we can link those moles up into volumes. So it looks like this. If each balloon is the same volume, we need 1 volume of nitrogen, coefficient of 1, 3 volumes of hydrogen, coefficient of 3, will form 2 volumes. There should be a 2 here. Really? Oh my gosh. Yeah, this should be a 2 there. Where'd that go? 2 moles of NH3. Okay, so this actually are the 3 gas laws we talked about. The most recent one, this one is Avogadro's, links volume and number of moles. This one's Charles, I don't know if you remember, links volume and temperature. The fact that we have them both on the same side of the proportionality symbol means that as one goes up, the other goes up. As one goes down, the other goes down. Now we have an inverse relationship, according to Boyle's law, between volume and pressure. I usually kind of think monkeying with the volume has what consequence on the pressure. Well, if I picture a gas, and if I picture I decrease the volume, I'm going to increase the pressure, okay? And then if I expand my volume, my pressure is going to go down. So they have an inverse relationship like that. So we can join our volumes, and they look like this. We're actually going to try it. We're building up to the ideal gas law. And we said that if you have a proportionality between 2 quantities on either side, you can swap out that proportionality symbol with an equal sign if you introduce a constant. And so it looks like this. Okay, so now we're not proportional, we're actually equal to. Introduce a constant that we're going to call R here in a minute, but we'll call it K for now. So if we rearrange this, or I think we're not going to, rearrange this to get the constant by itself, this is the situation with all gases. All gases. Pressure times the volume of the gas divided by the number of moles times the temperature, and the Kelvin scale will equal some constant K. So like I said, K is all well and good, but it's not nearly as special as R, a pirate's favorite constant. Okay? So R is called the ideal gas law constant. And remember your final exam, you get to bring a sheet of paper, and you might want to put the value of R on there. I'm just thinking. Sometimes I give it to you in your final, sometimes I don't. So it has an actual value. This is has R by itself over on the right. This is what I call the flattened out version. So actually these are both the same thing. I mentioned that I like to list these in a certain order, and they're according to this. And it almost sounds like it could have like a little song, PV equals nRT. It's kind of like the Q is equal to MC, so P delta T. So it's kind of got a rhythm to it. Okay, PV equals nRT. Ideal gas law equation. So this is actually kind of like, speaking of thermodynamics, like back to kind of like physics almost, where you plug and chug. A difference you might run into in this class versus physics, although you should do in physics too, but not all physics teachers emphasize using units. So we're all about units in here. So if on that last part of your final exam, if you have a test or if you have a question that uses the ideal gas law, it's an ideal gas law problem, you should use units everywhere. And you'll see it's what we call dimensionally consistent. So what does that mean? Well, pressure, you can go, and actually years ago when I first learned this at the University of Northern Iowa, we went with millimeters of mercury, mmHg. But here we're going with units of atmospheres for pressure, okay? So if we go units of atmospheres for pressure, of course V is going to be in liters, N is number of moles, T is always going to have to be in the absolute temperature scale. Then actually the way this works is that our R will have a value of 0.028058, and the units of R will be liters atmospheres per mole Kelvin. Okay. All right, so let's do a problem. Like I said, there just seems like there's a lot of problems now. PV is equal to nRT. I think I'll write that at the top of my board. So the way I do these, I should have just left my box up there. Well, maybe I'll try to draw a better box. Okay, here's my gas of interest. Notice for a lot of problems, or you will notice, not this one, but I don't care what the identity of the gas is. This one I do. Okay, so the gas will behave, as long as it's behaving ideally, it will behave like this. And we talked about the two conditions means that, let's see, the two conditions means that the volume of the particle is basically zero, negligible compared to the volume of the particle, yeah, it's negligible compared to the volume of the container, and that there's no connections between those gas particles, no intermolecular bonds. All right, so then I usually start lifting. I do this and see what I got for my problem. So what volume will occupy, question mark volume, and notice this is very common. If I read this a few times, N isn't given, but mass is given, and the identity of the gas is. So for N, I'm going to say from mass and molar mass. Let's see. And I'm going to go ahead and say mass was 0.20 grams and molar mass of CO2. So we know how to do that. It goes ahead and gives my pressure in terms of millimeters mercury. You're like, really? You couldn't go ahead and fix that for me? But you guys just did some problems that you handed in where you know how you can go from millimeters of mercury into units of atmospheres. No problem. Recognizing 1 atmosphere is equal to 760 millimeters mercury. We can do that. And it gives me my temperature, 22.0 degrees Celsius. You're like, really? Well, we know we can add 273.15 and get it to the Kelvin temperature. So it's kind of like on the front end, we have to do a few little problems. Happens all the time in chemistry. So bottom line is, if you have one equation, you can solve for one unknown. And that is exactly what we'll have. Because we have pressure, volume, we'll have number of moles, we have R, of course. Wait, don't have volume. We're solving for volume. We have number of moles and we have temperature and R. So that's it. So what I like to do is rearrange this ideal gas law equation, solving for, I put the variable I want to be left with on the left. And so if we rearrange it, we can get volume is equal to nRT over P. And I do that on the front end. I've seen some students over the years who like to kind of plug in first, but I like this way. And then I'm going to remind myself that R is 0.082058. And units are liters, atmospheres, oh goodness, per mole Kelvin.
Could you go back to that last slide for a second?
I can. This one?
Yes.
Yeah. And this step is actually a very common step where we all make mistakes. I do too. And it's just basically taking the flattened out version and taking it into what we're going to substitute into. So if we want to isolate volume, we're going to divide both sides by pressure. And that's why it ends up like nRT over P. Very common mistake. Okay, so again, just to, I kind of mentioned this as we were kind of dissecting the problem. We need to convert millimeters of mercury to atmospheres just because we're using that value of R. There is another value of R out there with millimeters of mercury, liters per mole Kelvin. And we need to get to number of moles from the mass and the molar mass of carbon dioxide, and we need to fix the temperature. Like, oh, drat. So here's going to get to N. So we need to knock out the molar mass of CO2. So that's 12.01 plus 2 times how much oxygen weighs, 16.00. And sometimes we've done enough with CO2 with like combustion analysis. The molar mass of CO2 is 44.01 grams per mole. Then it's all about taking that mass, which was 20 grams, and the molar mass, and getting to moles. So the first term is going to be that 22.0 grams. What's the next term going to be?
1 mole over 44.01.
Yep, 1 mole over 44.01 grams. How many sig figs, guys? Fingers. It's like we're back to the first part of the course. Yeah, 2. So you're looking at N is 0.0045 moles. Getting ready for the comprehensive final on Monday, it'd be like, oh, some of that stuff that I struggled with, you're probably like, I just know it, like that's back of my hand. Okay, so there's our N. We need to fix our T. And again, you might want to jot this on your note card, or you guys get a whole sheet of paper on both sides. How do you get from Celsius to Kelvin? You're going to add 273.15. So we're going to round this to decimals. How many decimals? Just 1. Yep. So 295.2 Kelvin. And then if I was doing this problem, I'm not going to necessarily kind of belabor it, but I would be jotting them down. I like to doodle, you know, kind of updating my little box, things like that. Now, it's my problem, not yours, but remember we talked about how if you leave numbers unrounded, you actually, if you have a series of calculations, you get a more solid answer in the end. But rounding is good because then you remember how you're supposed to round. Okay. So we got to fix this one. So if our first unit, if we're going from millimeters of mercury to atmospheres, what's the next term? You guys just did this on homework.
1 atmosphere over 760.
Yep, 1 atmosphere over 760 millimeters of mercury, mmHg. Actually, this is an exact relationship right here. So we're limited to 3 sig figs. So you're looking at 0.963 atmospheres. All right, is that about it? I think so. Now we're ready for the plugging and jugging part. But we have to include our units. So remember we said that volume is going to be nRT over P. So here we go. In the numerator, we're going to have 0.0045 moles, and sometimes, and I'll go ahead and show you what I mean, I actually put it's going to look silly, but I will put the moles over 1, and the reason is the units that are near R actually is units of liters atmospheres per mole Kelvin. So then if I do that, my units kind of cancel like they're supposed to. So the next term is R 0.082058 liters atmospheres per mole Kelvin. And since I put this first unit, I put N over 1, then I can see my moles cancel. And then in terms of our Kelvin temperature, we came up with 295.2 Kelvin. And I see my units of Kelvin cancel. Okay, so it's looking pretty good. I have units of liters atmospheres. And in the denominator, when we converted the millimeters mercury In units of millimeters of mercury to units of atmospheres, we came up with 0.963 atmospheres. So that's pretty good. Atmospheres canceled. And I think I've mentioned, I know, earlier in the course when we talk about canceling units that this is a way to kind of give you confidence that you set it up correctly. James tapping in his calculator. So how many sig figs? Multitasking. I'm thinking only 2. Ding, 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 ding. Yep. 0.11. And units, of course, would be liters, which is awesome because that's the only units that didn't cancel. So now that's your classic, and as you might imagine, we could, mix it up. Instead of a question mark for volume, we could have a question mark for pressure, volume was known, or we could have a question mark for temperature, okay? And then don't forget that if you're working a problem where you're supposed to get to the temperature, how do you go from Celsius? We went from Celsius to Kelvin. How do you go from Kelvin to Celsius? Subtract 273.15. Was not a trick question. Okay, so let's do another one. And it's not so, I'm going to kind of show you some little nuances that you might run into. I like gas law problems. And so let's see if you guys too do when you have to do 10 billion of them. I don't think there's 10 billion of them, but they'll be due Wednesday. And they are real problems. Okay, so this one's a little bit different. I'll just go ahead and erase my question mark there. Erase this information. Okay, I'm going to go ahead and, I should have on the last one, I will on this one. I'll go ahead and buy my box and I'm going to go ahead and say my gas is argon. That's the pirate's favorite element. Oops. All right. And this one says, what is the density? Well, I'll come back to that, but it gives me my temperature, 25 degrees Celsius plus 273.15, but what's the point since you don't have any decimals there. Pressure, well, that's nice, 1.22 atmospheres. That was nice of them. Okay, now notice that these are both, don't have them. But the problem, what we're supposed to get to, our goal is to find what's called, there's 2 types of densities. This is the mass density, grams per liter, and there's also molar density, moles per liter. And do you see where I can use these guys, I'll do it this way. I can do these guys to get to what we call the molar density. Oops. Units will be moles per liter. Does that seem right? I'm not gonna solve them individually. I'm gonna come up with a ratio. And then once I have that, do you see where I could go from moles per liter to grams per liter? That's not too bad. How am I going to do that? Molar mass, mm of AAR. Exactly. So that's how we're going to work this one. So ideal gas law, and in this case we're going for a ratio of N to V. So again, I miss this all the time. So we're gonna divide both sides by V, and then kind of both sides by RT. Okay, I don't know how you guys, I'm not a math teacher, sorry. But I can picture that. You guys okay with that? Okay. It's the one you're about to go. So here in a minute, all we're going to do is plug in our pressure of 1.22 atmospheres, our R, and we're going to plug in our Kelvin temperature for T. So we got to fix our Kelvin temperature, or excuse me, Celsius temperature to Kelvin, so we can take 25 degrees Celsius. Again, 273 is the same thing as 273.15 in this case because you don't have any decimals associated with the Celsius temperature. You're looking at 298 Kelvin. Plugging part looks like this. So again, this is what we call our molar density, N over V. So in the numerator, we have our pressure, 1.22 atmospheres. Again, units are important because we're going to see if we get the units we think we should get. In the denominator, we have R and T. R is at 0.082058 liters atmospheres per mole Kelvin. And then our Kelvin temperature was 298. So let's check out our, by the way, we have a lot of 298 Kelvin temperatures because actually it's 25 degrees Celsius is the standard conditions for gases. Okay, so units of atmospheres cancel. Units of Kelvin cancel, and we're left with something that's a little odd. We have no units in the numerator, and in the denominator we have units of liters per mole. Again, I'm not a math teacher, but what I know is if you want to bring what's in the denominator, liters per mole, up to the numerator, up to the normal level of things, you basically flip them. So actually this is units of liters per mole. Oh, sorry, moles per liter, final answer. The flipped version. Okay, 3 sig figs. So you're looking at 0.0499 moles per liter. Not quite done yet though, because we want a density, not the molar density, but the mass density. So we go to the periodic table, find the decimal number for argon, which is 39.95, and use that to our benefit. So how can we use 39.95 grams per mole to our benefit? Do we use it like that or do we flip it? 39.95 grams per mole. How many people think we leave it like that? I do too. And then our moles cancel. We're left with units of grams of argon per liter of argon, which is exactly what we wanted. I bet you guys would tell me 3 sig figs. So you're looking at 1.99 grams per mole. So that's the density, the mass density. Just hop, jump, skipping along. Okay. Well, what else do we have that might be kind of a little different? Well, here's one for you. So let me erase a few things here and rewrite what we got. Let's see. Well, moles aren't given, but mass is given, so I'm going to go ahead and put the mass there for now. 1.007 grams. It doesn't say it's an unknown gas. It says the pressure is 15 millimeters mercury. So you're like, drat, I have to convert that. And you will. We're going to have to convert that to units of atmospheres. No worries. And it gives me a volume is 452 milliliters. You're like, oh, are you serious? But you have to show all of your work on your final exam, just like all your homework on your unit exams. In order to get full credit, you're going to have to show that conversion. We can do that. Gives me temperature in degrees Celsius. You're like, can I not get a break? Okay. And in this case, you're like, well, I have a number for everything. Well, you do. But notice that we don't know what the gas is, and so we can't use a molar mass to go from mass to moles. So you're like, drat. But the whole point here is, what is the molar mass, question mark, molar mass of the gas? Units for molar mass are grams per mole. So here's the deal. If we make mole is what we're after, okay, then all we got to do is take that grams divided by the moles that we get, and we have the molar mass. Does that make sense? That's exactly what we're going to do. Now let's see what I mean. So we're going to solve for N first. Divide both sides by RT, and you get N is equal to PV over RT. Again, a very common mistake. I see it a lot. N is equal to RT over PV. And by golly, when people go to make multiple choice tests, they will give the distractor will be the inverse of the right answer. Okay, so let's see what we need to fix. Gotta fix our millimeters of mercury. So we can take that times 1 atmosphere over 760 millimeters of mercury. Remember, that's an exact relationship, so that we're allowed 3 sig figs with our atmospheres. So you're looking at 0.941 atmospheres. Let's see, what else do we need to fix? I need to fix our temperature. It wasn't 25, it was 23, a little colder. So the 23 degrees Celsius, if we add 273.15, we get 296 Kelvin. And then don't let this throw you off, we have to fix our volume too. And we've been doing this since like the second week of class. We take 452 milliliters times 1 liter over 1,000 milliliters. And you move the decimal place over 3 places, 0.452 liters. All right, so you can kind of see where these 3 numbers, the pressure, the temperature, and the volume, are going to go up here. Pressure, temperature, volume. On the next slide. So it looks like this. N is equal to, in the numerator, we have 0.941 atmospheres. Also in the numerator, we have that 0.452 liters. And in the denominator, we have the R, 0.082058 liters atmospheres per mole Kelvin. And then also in the denominator, we have that Kelvin temperature, which was 296 Kelvin. So we should have everything cancel except for units of moles. Now it doesn't count if you say I need moles left over and you just circle moles and you're like, well, looks good to me. But if we see what cancels, it is good actually. So atmospheres and liters in the numerator cancel with atmospheres and liters in the denominator. Units in the denominator of Kelvin cancel with units in the denominator of the denominator for R. And then we're left with kind of, it looks like this, 1 over moles, basically. And it's what I said before. If I want to go ahead and resolve this, I can take the 1 over moles, bring it to the top, and it is moles. Moles over 1, so 1 over moles. So units of moles is great. You tell me 3 sig figs, and you'd be right. So you're looking at mole-wise of this unknown gas, 0.0175 moles. So then to get to the molar mass is grams divided by moles. So I'm going to go back to this number, and I'm going to divide it by that number. Okay, so for this particular gas, in that box, 1.007 grams is equal to the 0.175 moles. Oh, wait a minute. Typo. 1.007 grams is equal to 0.0175 moles. My bad. That's better. Okay, so the molar mass, 3 sig figs, gives you a molar mass of that particular gas is 57.5 grams per mole. I know you guys hate to hear this. This is a classic. It's a classic. So. And then you could have a follow-up question that actually gave some possible gases, and you'd have to maybe calculate more masses and match it up with a 57.5 grams per mole. But we're not going to do that. Okay. Something else. And this is one when we did thermodynamic, the unit of thermodynamics, I said, this might be a topic that you didn't necessarily get as exposed to in high school or your previous chemistry as some of the other topics. I hope you probably covered gases. So someone's like, oh yeah, this looks familiar. Okay. But anyway, at the time I said that standard conditions for thermodynamic problems are different than standard conditions for gases. In fact, on my sheet, if I was going to bring to my test next Monday, I'd probably write down standard conditions for those two, just so I didn't have to concentrate on it. So standard conditions for gases are the temperature is 0 degrees Celsius. I said 25. That's thermodynamic problems. 0 degrees Celsius instead of 25. And 1 atmosphere instead of 1 bar, which those are similar. Okay, so STP, standard temperature and pressure. And then here's one for you. I'll go ahead and kind of clean this up a little bit. I bet you guys buy this. If I'm saying STP, and it sounds like a fuel additive. If I'm saying that means that you're at 0 degrees Celsius, which is 273.15 Kelvin, and you're at a pressure of exactly, I don't care how many zeros you want to put it, exactly 1 atmosphere. Okay, so hold that thought. If, and we can do the math here, it's not too hard. If we go ahead and do one more thing, set N is equal to 1 mole, then the thing that's not set is the volume, which we can figure it out by plugging in and coming up with the volume. As it turns out, this volume would be 22.414 liters. Does that make sense? And then so this year I finally chased it down. So a while back I got this ball, and this is an adorable beach ball. Notice it says 1 mole is equal to 22.4 liters. So that the point would be that, assuming this is a volume of 22.4 liters, which that's what I'm going to argue here in a minute, then if you had, if it was under it's 0 degrees Celsius, which is kind of chilly, that's kind of cold, that's 32 Fahrenheit, right? If it was 32 Fahrenheit, 1 mole pressure, the pressure would be 1 atmosphere. Does that make sense? So I Googled it. 22.4 liters is about 6 gallons. And I'm like, that is so not 6 gallons. And then I grabbed the biggest beaker I've got. It's still kind of wet from soaking in the sink. But so if you're talking 22.4 liters. Wait. Okay. Yeah. This is like, it's just not right. Okay, because this is like 3 liters, this line right here. And so you'd have to take, it's just not right. Makes me mad. I have to go buy one that makes really 22.4 liters.
That would be a big bowl.
Yeah, well, I'm into that. This is just not it. Oh, it ain't. I guess they're bad right now. Okay. So I will remove that prop because it is not right. But what does that mean? Standard temperature and pressure. Okay. So this was the one that we started with. This would be 1 mole, wouldn't it? Because the molar mass of helium is 4.001. So 4 grams is 1 mole. I imagine the molar mass of ammonia is about 15. 15 grams is 1 mole. Of course, you guys would tell me molar mass of oxygen, molecular oxygen is 32.00 grams per mole. So we have 1 mole here. And that can come in handy. All right, what other variations do we have? And we're going to actually come back to standard conditions on a problem we have for the next part. Well, here's one. This is kind of fun. It's called the combined gas law. And there's various versions of this. I'm going to show you the most general version of the combined gas law. And the combined gas law works like this. Basically, when you see a problem, you're going to recognize it starts as, I call it state 1, and then it moves to state 2. And between state 1 and state 2, you have the number of moles of gas in your isolated gas continue to be the same. So if that's the case, we can take the number of moles and take it over with our other constant. Okay. So pressure, volume, and temperature, even if we change one of those, I don't know if this makes sense, as long as N stays the same, the product quotient of those 3 variables is going to have to stay constant. You probably recognize it to look something like this, where state 1 is here's the pressure, volume, and temperature at state 1. Here's the pressure and volume temperature at state 2. P1 V1 over T1 is equal to P2 V2 over T2. Okay, and it's easier to show you than to describe it. But as you can see here, to my math, we're looking at 6 variables. Those are real variables. So basically, you're going to know 5 of those, and you're supposed to solve for the 6th one. Very easy to make a mistake in using combined gas laws. And here's another hitch for this P1V1 over T1 is equal to P2V2 over T2. Let's just say that your temperature is constant too. Your T1 and T2 are the same. Well, then you have P1V1 is equal to P2V2. So they can start disappearing. Okay, what if your volume is the same? Well, then P1 over T1 is equal to P1 over T1 is equal to P2 over T2. Again, it's easier to show you than to kind of explain it. So in my, you guys are, I'm sure it's been a while since I've done the answers for the homework that you guys are going to turn in Wednesday. I imagine you guys are going to do one of these. When I do one, I usually write 2 boxes, and I call this state 1. Okay, it's the same gas, same number of moles, and so I have over here P1, V1, T1, and I have over here P2, V2, T2, and they are related by P1, V1 over T1 is equal to P2, V2 over T2. Okay, good. And then I just start lifting numbers. Now, this is different in that we aren't using R. No R. And that actually has some cool consequences. Since we're not using R specifically, and let's see if you can kind of, if you do, you'll see, well, that makes sense. Our units of pressure can be anything, and our units of volume can be anything. But our units of temperature have to be Kelvin. So let's see what we got. Let's see. State 1, T1 is 12 degrees Celsius. Of course, we're going to have to go to Kelvin. P1 is 322 millimeters mercury. V1 is 33.5 milliliters. So again, did you catch that? I don't have to convert these guys. As long as they're the same in my state too. It's very fun. Temperature change, so the gas now occupies, now it's going to be T2, so T2 must be question mark. But it says that after the temperature was changed and my new volume, so that means my V2 is 46.7. And my P2 is 353 millimeters mercury. Cool. So that's not bad. And if you're like me, you're like, yuck. I'm going to tell you how I'm going to get T2 by itself in my non-math lingo. Okay? T2 is what we're after. And I'm going to basically rearrange this. What I do is I have 2 ratios. I cross multiply to flatten it out. Let me show you what that means, looks like. So I'm going to say P1V1 T2 is equal to P2V2 T1. That's my flattening out. And if I do that, I've got a fighting chance to get the algebra right. Okay? So again, we're going for T2, which is right here. So if I divide both sides by P1V1, then I'm golden. So T2 is equal to P2V2 T1. And I'm going to go ahead, and sometimes you'll see it this way. I'm going to go ahead and put my P2 over P1, my V2 over V1. You know, I don't know. It's all the same thing. So that's it. Okay. So what I built on the board is exactly this. Is it okay if I go on?
Yeah, that T1's in the numerator.
T1 is in the numerator, yes, yes. T1 is definitely in the numerator, yeah. Good question. All right. Got to clean up our temperatures. Don't get caught. So the temperature we're converting is 12 degrees Celsius. So if we take 12 degrees Celsius plus 273 units, because there's no decimals there, don't need 0.15, you're looking at 285 Kelvin as the initial temperature. And I can't remember, I'd have to go back to the original problem, but did it want the temperature in the Celsius scale? Or did it say?
Yeah.
Okay. So we're gonna have to subtract 273 from the calculator. So here we go. Yeah. See, I even write it different here than I do over here, so I don't know. This is this. They do the same thing. I don't really like this. Instead of that, I probably would have just kind of made one big old divisor and then put the, anyway. So let's plug. Here we go. Oh, I see. I did it in the next one. Okay. Good with that. And here's where it really pops out at you, like, oh, pressure, as long as they're millimeters of mercury, hey, they cancel. Volume, milliliters, they both cancel. Okay, but your temperature has to be Kelvin. So it looks like this, where the first ratio is going to be our P2 over P1. So that's 353 millimeters mercury over 322 millimeters mercury. And our volume is going to be V2 over V1, which is 46.7 milliliters divided by 33.5 milliliters. And in terms of units of Kelvin, we came up with a Kelvin temperature of 285 Kelvin as our initial temperature. 3 sig figs. So, and too many numbers, my fingers get fat sometimes, and they, so, you know, a good strategy would be on a test to run it through your calculator and then write it down and run it through your calculator again and make sure your number matches. So in terms of Kelvin temperature, our T2 is 436 Kelvin. And you guys told me, how do I get to Celsius? Minus 273, yep. So T2 is equal to 436 Kelvin minus 273 units. So you're looking at 162 degrees Kelvin. Okay. So I'm going to go ahead and start the next unit. I don't think I'll get through it. Not unit, sorry. There's no unit 6, the next part. Oh, wait a minute. Yeah. Oh, I guess a few more slides. Okay, like I said before, this combined gas law actually changes up. If T is held the same, it looks like this. That's what I tried to say. If volume is held constant, then that term drops out. So you have a ratio of pressure to temperature, like this in state 1 and state 2. Okay, one last one. If pressure is held constant, then you have the relationship between volume and temperature like this. So they're all versions. What well, in an ideal world, we wouldn't have had a snow day, but so we're gonna go ahead and start part 3. Like, really? Yes, really. Because as much as possible, I'd like to, when it comes to Thursday, I'd like not to have to be doing any lecture, but that will be my makeup day if we don't get through the stuff.
So how big can the sheet?
How big can the sheet be?
Yeah.
Like an 8.5 by 11, like a regular piece of paper.
Okay.
Yep.
So I can just bring a piece of paper.
Just bring a piece of paper.
Okay.
Yep.
I forget you said it's front and back.
Front and back, yeah.
Front and back.
Yeah, front and back. Would it help? Because some years, I think instead of just a blank piece of paper, I've had you able to bring my favorite periodic table. You can't pick your own periodic table, but you know that black and white one, like this one. Yeah, like this one. Would you rather have one of those so you can mark it up, and then as one side, and then the other side's free, so you can write the margins of that side, and the other side you write it to the back. I'll bring some. I'll bring some Wednesday in case you want to. Or stop by my office and I'll give you one if you want to start marking up. an advantage to having your periodic table, what comes to mind is the whole +1, +2, -1, -2, and kind of drawing it that way. You know, doodle blocks. Okay, so I'm looking at 4 minutes or so. Let's see what we got here. This is another fun topic. To me, when I was getting ready for lecture over this part, I was like, that seems like titrations. Let me show you what I mean. I can take this information from the words up there and put it on the balanced equation. So, what volume of H2 gas, so I find my H2 gas, I put question mark volume. And notice it gives me some more stuff. This stuff is about my H2 gas. So my H2 gas, I'm going to put volume is equal to, or question mark volume. Notice I'm going to say T is equal to 22 degrees Celsius. P is equal to 1 atmosphere. Okay, so that's all about my hydrogen. Can be produced using 2.50 grams of zinc. So I find my zinc, I put 2.50 grams and excess HCl. And we know what the importance of that is. That means that your limited reactant is zinc. So does this, I bet you guys will buy this. Do you see where I can go from grams of zinc, of course, to moles of zinc? I'll put N here. I can go from moles of zinc then to moles of hydrogen gas using stoichiometry. This is balanced set of stoichiometric coefficients. And then once I have moles of H2, by golly, I have moles, pressure, and temperature. I can knock out volume using the ideal gas law. That's just it. So it looks like this. So we're going to go from moles of zinc to moles of hydrogen gas. Oh, my bad. Okay, yeah, that's okay. So from the periodic table, the molar mass of zinc you'd find is 65.39 grams per mole. So 2.50 grams of zinc times 1 mole of zinc per 65.39 grams of zinc. 3 sig figs. Now you're looking at 0.0382 moles of zinc. And now you'd be like, well, all right, stoichiometric coefficient is 1 to 1, so I got it. That's the moles of H2, and you're right. But don't forget to show that. So the way we know to show it is we would take the moles of zinc like that, 0.0382 moles of zinc, and we'd multiply it by 1 mole of H2 over 1 mole of zinc. And we would get 0.0382 moles of H2. And now this really kind of becomes what we've talked about this afternoon. So if we look back now at what we don't know was volume. So if we solve for volume, we divide both sides by P. It looks like this. Volume is equal to nRT over P. And I think we have some cleaning up to do though. The temperature we're given was Celsius, so we have to take our 22 degrees Celsius, add 273 units to it. You're looking at 295 Kelvin. I think that was the only fixing up we need to do. So here we go, plug and chug. From stoichiometry, we got the volume of H2, or sorry, we got the number of moles of H2 was 0.0382 moles. R is well, you know what it is, 0.082058. Units of R are liters atmospheres per mole Kelvin. The Kelvin temperature was 295 Kelvin. And the denominator, all we have is the pressure, which was 1.00 atmospheres. So unit-wise, you're looking at moles to cancel, Kelvin to cancel, units of atmosphere in the numerator of the numerator cancel with units of atmosphere in the numerator of the denominator, and we're left with units of liters in the numerator of the numerator, which is right. 3 sig figs. And so at that pressure and temperature, you would expect your H2 gas that's produced to occupy a volume of 0.925 liters. And that will be a good place to stop. So we'll pick up here on Wednesday.